Good morning, BWSI. How are you today? All right. And what is BWSI? Excellent. Thank you very much. I think we're going to have a full house today. Our speaker today is Professor Cynthia Breazeal from the MIT Media Lab. Has anybody looked or researched any information from the MIT Media Lab? Go ahead.
We wanted to go, but they didn't let us.
Well, maybe Professor Breazeal can help organize something later. No pressure. No pressure. So, but she's going to hear and talk to you about some of the work she's doing in artificial intelligence as well, and what the Media Lab is looking at. I think if you do any research on the Media Lab, you'll find out that there are people there that have tons of great ideas. And the ideas are so far out there that people say that will never catch on, like touchscreen displays. When they were invented at the Media Lab, everybody said, that'll never go anywhere. And look at us today. I bet every one of you's got one of those touchscreens, and it better be in your pocket, right? In your pocket. Anyway, so let's hear it for Professor Breazeal, and let it get started. Thank you.
All right, can you, oh good. So it sounds like the mic's on, yeah? Okay, great. So it's great to be here. I wasn't going to talk that much about the Media Lab. I was going to talk more about my work. I direct the Personal Robots group. But the Media Lab is known for being what we call a radically multidisciplinary lab. So we have people who do computation and music. So those of you who know Guitar Hero, the two PhDs who graduated from Media Lab created the technology for that game. We have people doing CRISPR technology. We have people doing neuroscience, optical controlled neurons. We have a lot of stuff in human-computer interaction. So it is, very, very broad in what we do. And we use the term anti-disciplinary to basically say a lot of the most creative ideas happen in between the space between traditional disciplines. So when you go to university now, you all major in X. I think we're moving into a time where a lot of the world's most challenging problems are not solved by single discipline, but across disciplines, and not just people bringing the disciplines they know, but actually creating a new discipline across disciplines to address those problems. So social robotics is an example of one of those disciplines. So I got my PhD here at MIT in 2000, and I'm credited by founding the field of social robotics and human-robot interaction. So when I started my work as a PhD student, the idea of autonomous robots, the value proposition was robots could do the dull, dirty, and dangerous tasks far from people to keep people safe. So things like exploring the oceans, going into volcanoes, even going to Mars. And for my PhD, I basically asked the question, if we can send robots to Mars, why aren't they in our homes? Why aren't they in our living rooms? And just acknowledging that at that time, it was very much like when, big, huge mainframe computers were technologies that only trained experts knew how to use. And then people started thinking about what would it mean to bring a computer onto every desk on every home. So that was really the shift that I would say created social robotics, the field of social robotics. So it's the question of how do you design autonomous robots that anyone, regardless of their expertise, can interact with and get value from. And a lot of the key insight of that was to say, well, maybe the most universal interface is the social interpersonal interface. And we already knew from science fiction and all these kinds of areas, people already anthropomorphized robots. They already treated robots not as mechanical entities, but as psychological entities. But at the time I started this work, so much of it was focused on manipulation and navigation and vision, and people weren't thinking about the deep intelligence we have around social and emotional intelligence that allows us to collaborate and communicate with one another. You're doing a lot of teamwork. Imagine if you could only work by yourself, how much you'd be able to achieve. Everything we see around us is really because of our social intelligence and our ability to collaborate and work together to create more and be more than we could if we were alone. And so now, finally, after 20 years, the field of robotics is catching on and saying, oh, actually, maybe it's robots with humans that actually really matters, not just robots doing their own thing. So how you create robots with social and emotional intelligence to really coordinate and be teammates for people is a lot of what drives my research, and it's starting to drive more and more research across my field. But today, I'm going to talk about two particular thrusts to my research. They both have to do with artificial intelligence and education. So there's a lot of work that my group has been doing around creating autonomous social robot learning companions for young children, so personalized learning systems that are really designed to interact with young children, and young children often learn through play. So how do you design robots that can help children learn through interacting and play? And the other thrust I'm going to talk about is, well, we are now living in this world where AI, I'm sure as you know in this room, is permeating everything. It's going in and transforming the workplace, disciplines, at an unprecedented rate. And yet right now, AI is a field that you only learn once you come to university. And it's controlled only by kind of the powerful institutions that can hire people, like you're growing up to be. And if we do that, I think we risk a future where AI could exacerbate the prosperity divide rather than close it, right? We're already feeling the tension of that in our society today. So the only way you address that is democratization through education, right? So the question here is, what does it mean to create an AI literate society? So far more diverse, inclusive group of people, not just those going to colleges, but those going to VOTech, workforce retraining, all feel comfortable that they can create value with these technologies. And so that's a big initiative I'm leading across MIT. I'm sure many of you know we are the birthplace, or one of the birthplaces of artificial intelligence. We obviously do cutting edge research in that area today. We're also the birthplace of constructionist learning, right, with Seymour Papert and with amazing platforms like Scratch and App Inventor. So all of that came from MIT. So the question is, can you bring in these cognitive services, these algorithms, and put them in the hands of kids so that kids can not only learn about AI, but create projects of their own passion with AI, and with that learn about the societal and ethical implications of AI, because I'm sure if you've been listening to the media, there's a lot of concern, there's a lot of fear, and there's a lot of misunderstanding of what AI is and what that means for people. So we as MIT are trying to step up to that and say the only way you address this is by showing a far more diverse group of people that they can come along and be successful in the era of AI. It's not just for the elite. So that's what I'm going to talk about. So artificial intelligence. Artificial intelligence as a field has gone through many summers and winters, meaning there have been periods of extreme hype followed by disillusionment because, of course, it's very hard to ever live up to the hype that can be created around any kind of technology. So I have seen 2 summers and winters. We are definitely in a summer right now with deep learning. So there's a lot of confusion now about what AI is. When I talk to kids today, what do you think artificial intelligence is? They think it's robots. They don't realize that Snapchat and YouTube recommender systems and Google search and all of these things are AI that's come into their life and that they're touching it every day. So this is really important because you have to know what AI is, how it's influencing your life. It's coming into people's homes now with smart speakers. We're starting to live with AI in a way we never have before. Young children to our oldest citizens are starting to talk with intelligent machines every day. So I say, children born today, they're not just digital natives anymore. Children born today are AI natives, right? They're growing up in a time where they've always been able to interact with intelligent machines. So this is really important. It's really important that we understand this, we understand the social implications, and we try to, again, educate people about what AI is. I'm throwing up the definition here that the AAAI offers. It's not just deep learning. It's way more than that. And I'm sure in a number of the projects you're doing now, you're touching AI already. So it's about creating machines that essentially do things, reason, make decisions, learn, that if people are to even argue animals were to do it, if you saw a machine do it, you would say that's intelligent, right? So it's an incredibly broad field. The thing that's different is that machine learning has really come up and has created, machine learning plus big data has enabled real-world applications that's really disrupting the workplace and how tasks are automated. That's kind of the new. So machine learning has become much more prominent in this wave of AI, and particularly deep learning. But of course, the question is, what's after that? So there are a lot of people at MIT and around the world trying to understand the impact of AI on the economy, on society. And one of a very famous economist in the Sloan School of Management here at MIT is David Autor. If you haven't listened to any of his lectures, I encourage you to do so. So he's been studying multiple industrial revolutions driven by technology. We're like in the 4th one now. And his question is basically, if technology automates jobs and tasks, why are there so many jobs? Shouldn't more people be doing leisure or other things if the machines are supposed to be doing more and more? And the punchline is, we are such a creative species. We continue to create and innovate and create new jobs and new industries that if you were someone in the time of the farming revolution, right, there are jobs today you would never even be able to fathom, right? So that this is the trend we've seen. The question is, what's going to happen with AI? And the argument is, when you're thinking about what people need to know and be in a future where we're increasingly living and working with these kinds of technologies, creativity is going to be paramount. Humans have to learn and become creative thinkers and doers. I think empathy is going to become increasingly important. I don't know how many of you are aware of this, but there's been meta-analyses of empathy in this country with college-age students. And since the year 2000, over 30 years, it's been in a precipitous decline. It's hard to imagine we can have a thriving democracy if we can't empathize with one another, right? So empathy is going to be incredibly important. And the ethics, right? We're seeing examples of AI being trained with data that's reflective of the biases we have in society today. And lo and behold, this is creating AI decision-making systems that perpetrate that bias against minority groups, against women, in an unintended way. But we're starting to understand that. So the ethics of AI, and you now becoming designers who have the frameworks to be able to think about the ethical implications of what you build, is going to be increasingly important. You can't just rely on someone else trained in ethics to look at your stuff and say, okay, that seems to be not harmful or not. Better if you have the power and the tools to also think in those ways as you design these systems. So these are things that are going to be creative. Now, this is just, to think how far we've come and how society changes its, ideas of AI in education. This is from a Japanese magazine in 1969 of AI in the classroom. So, I don't know if this is a virtual avatar teacher or a video call with a teacher, but you have now there's no human teacher. There's, a screen teacher here. I like how the robots over here are like the disciplinarians. They're like whacking the kids to make sure they're paying attention. That's robotics in the classroom. We see all these kids with computers, et cetera, et cetera. So, I like to think that we've come a longer way to kind of have a more humanistic vision of AI in the classroom. Maybe not quite so much like this. But, we're always biased by what we create in our social norms. So, of course, the question around AI in education is, how is it going to potentially impact and transform education? And really, what does this mean, again, for preparing you for success in the era of AI? So, again, two themes I'm going to talk about today. Autonomous robots that play with kids to help kids learn, and then kids learning about AI, starting from literally preschool all the way up through middle school and beyond. When you think about how young children learn, it's very different when you're able to, say, sit in a lecture hall or sit behind a computer and type and read, right? Young children can't read. Young children learn through play. They learn through play with friendly others. And so it's fundamentally, it's not only cognitive, right? There's a deep interpersonal social component and there's an emotional component. And so we've been really fascinated and inspired by peer-to-peer learning, right? So there's a lot of computational, systems, computer tutors, where the computer acts like the teacher or the more knowing tutor and is modeling what the student knows and is shaping that in a very kind of more deliberate adult-like way. We've been fascinated by, well, what if instead of that, what if you actually built robots that was more like a peer-like companion for young children? So you play these educational games with children collaboratively like a peer, but under the hood, the AI is absolutely personalizing the curriculum, the scaffolding, everything the child needs to learn. So it is, in many ways, an Uber system trying to really get the child on the best path. But to the child, I say it almost feels like a Disney sidekick. It's the not quite human other that you can talk to, that you can play with, right? So it's a much warmer, friendlier experience with an autonomous tutoring teaching system, but it doesn't, again, feel that way. It's not coming across that way. So social interaction is key to how young children learn. Play is key. And so the challenge is, well, how do you create the behavior of autonomous robots that can actually engage in this very rich, sophisticated, complex, fine-grained interaction that people naturally do every day? It turns out this is like one of our superpowers. It is incredibly hard to do. We take it for granted because our brains have evolved for millions of years just to do it. Like machine vision, we took it for granted. We thought it would be easy to do. Decades later, we're finally starting to make progress. I'd argue social emotional intelligence, it's the same thing all over again. So now what happens if instead of a child and a child, you have a child and a robot, right? we often have a tablet that serves as a shared game surface. So the robot and the child can take the same actions on the game, and they talk and interact around what's happening in the game. So that's the paradigm we've been exploring. So social dynamics, it turns out, are really important. So the robot, you, of course, you are able to intuit the social and emotional cues of the person you're interacting with, and that profoundly shapes how you're going to interact and respond with your partner, right? You want to keep them engaged, you want to keep them interested, you want this to be fun for each other. So you're constantly reading these cues. So in the field of affective computing right now, there's been kind of like 3 main phases of this. The first has been what we call the interpersonal context. So literally images of faces or videos of just faces where you're just trying to recognize, is this person happy, sad, angry, disgusted, et cetera, et cetera? Are they smiling, right? So we call this kind of like, classic, 90% of affective computing papers are about this. But we need to go beyond this if you're going to do interaction, right? So more recently, there's been work looking at understanding social dynamics of 2 people as they interact, extracting the facial features, the body postures, what's being said, to infer this kind of intrapersonal context of, do they trust one another? Is there a sense of rapport, of affiliation that's forming between the pair, right? That's analyzing now not just the person in isolation, but people in dynamic coupled interaction. And then the third wave that's just happening now is to say, well, what if we talk about collaborative activities like storytelling? And I'm going to talk a lot about storytelling for the nature of the robots that we build, where now the participants are much more goal-directed, right? So if you're telling a story, you have a goal. You want to be engaging. You want to make sure the people are listening or following along. You're constantly sending and reading social signals to make sure that you are aligned on that goal. And as a listener of the story, you want to show that you understand. You want to show that you're engaged, right? So it's this intention-based interaction between the participants to make sure it's a positive experience for everyone. So that's an intentional context. So we're trying to build machines that can do this intentional context. So how do we do that? So again, we do a lot. We're inspired by peer-to-peer learning. So we literally, study how children share and tell stories to one another. And we're trying to develop computational models to emulate that, right? So
the cat broke the window, and then it ran through school and peeked inside.
So you can see the child listening is constantly giving back channels, laughing, they're sharing gaze. We study this over many children. We run affective computing algorithms to extract things like facial expression, body pose. We feed them into, in this case, POMDP algorithms. There's a whole bunch of algorithms that you could choose from to learn these models. And then we literally put that model in a robot, and we put that robot in the same situation with other children, and we look to see how does that robot's behavior compare to having a real child there. And not only that, but how does it affect the child's actual behavior, right? Is that child more engaged? Does that child tell longer stories, right? So that's the game, right? That's the game. So as we do this work, I mentioned that social robotics sits at the intersection of multiple disciplines. So there's obviously a lot of robotics and AI and machine learning that we do in the field of social robotics. There's a lot of psychology that we do in the field of social robotics. So this is to understand the psychology specifically, in this case, of how children engage and interact with a robot. That may give us additional insights in terms of how children engage and interact with people. So we can do science through this work, psychology, as well as advancing AI. And there's a lot of design. So that Tega robot that you saw, we built and designed that robot in our lab. It's an interactive squash and stretch character designed specifically to be appealing for young children. So it's at the field of arts and science and engineering is absolutely where social robotics sit. So we can technically assess how well that algorithm performs, right, in terms of emulating what a child would do, reading those signals from a child. But then we can also look at what's the psychological impact of engagement on the child who's a storyteller, because what we're trying to do is get this robot to propel the child's learning and engagement, right? That's really the goal. So what we're discovering is that these nonverbal cues really matter in a lot of ways. So we've done psychological studies basically looking at if you have a robot that has that model you saw versus one that's equally expressive but random in how it sends those cues, we see that children tend to tell their stories much more often to the contingent back-channeling robot with that more sophisticated model, right? So in terms of their behavior, they'd rather tell the stories to a robot that's engaging with them as an interested listener, as well as they tend to tell longer stories. So that's important. We've also been discovering that, again, we are such a profoundly social species that when a robot behaves contingently in this way with children, children naturally start to intuit that that robot is a more credible, knowledgeable informant versus one who's not. So we, again, have had two robots. Children interact with two robots, one with that more sophisticated model, one with where it's as expressive but, say, behaving randomly. You show a novel object. A child introduces a novel animal to the two robots. Each robot says it's a different thing. The question is, who does the child believe? Overwhelmingly, children believe the contingent robot. So if you want to design robots to be effective learning companion for children, you got to pay attention to these nonverbals because children are make all kinds of social judgments. Not only do I like this robot, do I want to play with this robot, but is this robot even credible, right? Do I even believe what this robot's saying? And children are making these assessments subconsciously, right? So these nonverbals really matter. That's the punchline. So another dimension that we've been trying to understand is, it's one thing to build a robot that over short encounters can help engage children, but what happens when now you engage with this robot over repeated encounters over months, right? So now you're talking from short interaction to long-term interaction. And this is really still at the forefront of our field. These are expensive technologies. They're hard to deploy. It is hard to run long-term studies with robots in the real world with real people. But when you can do that, you can look at things like personalization. And not just personalization like your name and things like that you might do on a website, but personalization like building models of assessing what is the skill of this child, what do they understand, how does that make the AI system under the hood want to personalize the content, but also how should the robot be personalizing its behavior, all those nonverbal cues, how it engages you to keep that particular child the most engaged and propel that specific child learning in the most effective way. And then how do we move beyond kind of rapport that we build from a short-term interaction to thinking about relationship? So we know that the better the relationship between doctors and patients, the better the health outcome for the patient. We know that the better relationship between a teacher and a student, the better learning outcomes for the student. Is that true for robots? So we have the opportunity to study that. So I'm going to show you a video just because you have to kind of get a sense of what this looks like in practice. We work a lot with Boston Public Schools. It turns out Boston Public Schools have roughly a 30% of their student body of kindergartners are coming from families who don't speak English as their native language, so they're English language learners. Now, we know the criticality of being ready to learn even when you enter kindergarten. If you start kindergarten behind, not ready to learn, it's very difficult to catch up. Often the children never catch up. We know that from standardized assessments right now, when you look at 12th graders, reading proficiency, there's only roughly 38% of high school graduating seniors in the United States high schools that read proficiently. Do you know a single scientist or engineer who can't read proficiently? I mean, this is a huge issue, right? So early intervention is key. You have to get kids off on the right foot, which is why we're spending so much time focusing on young children, so pre-K and kindergarten. So it's a 3-month intervention. We're doing it in real schools, which again is like cutting edge for my field. 60, 70 children with high bilingual or ESL populations. And we're comparing things like we've developed this personalization algorithm. How does it compare on children's learning to, say, a robot that's not personalized and follows a fixed curriculum versus a baseline of children who don't get a robot at all, right? Because we want to make sure that our algorithms are actually propelling the learning. So I'm going to play this video, and you can get a sense of like what the work looks like when you're really kind of digging into it. So the punchline is we have the robot learn a personalized policy from experience.
Name is
So reinforcement learning.
Nice to meet you. What is your name?
Ariana.
Early literacy skills form the basis of a large part of children's future learning. But children entering preschool and kindergarten come from linguistically diverse backgrounds, affected by many factors, including their family's cultural origin and socioeconomic status. Therefore, it's important to create personalized solutions for promoting early literacy.
What was your favorite story so far?
My favorite story, it was the bunny one.
Using a social robot as an embodied AI agent provides several advantages. Studies show that early literacy development requires exposure to a rich variety of spoken language and vocabulary during social interaction with others. Children engage with social robots in an emotive and relational way, and the affective cues that social robots can elicit from children provide a better opportunity to assess their engagement states. Our reinforcement learning personalization policy takes full advantage of these engagement cues. The robot's goal is to learn an action policy that maximizes the chance for each child to learn new linguistic knowledge while also promoting engagement. During the robot's storytelling, the robot models the child's listening behavior based on several features, including whether the child responds to the robot's question,
What would you see if you went to a rainforest someday?
Lions?
the length of the response, and also the child's facial affect cues during the robot's story. The robot's action space is the lexical and syntactic complexity of a sentence in the storybook. The reward function is a weighted sum of engagement and learning.
Frog when all is his pond.
The reward function was designed to reward new lexical and syntactic learning, but balancing this with engagement so that the algorithm doesn't always select a story with the highest linguistic complexity. Over the course of 3 months, we studied 67 bilingual and English language learning students from 12 local kindergarten classrooms. Students were divided into 3 balanced groups. The personalized and non-personalized groups interacted with our social robot Tega in a fully autonomous interaction in which the robot and child took turns telling stories. The robot either personalized its story choice or selected from a fixed curriculum. Children in the baseline group only participated in pre- and post-tests without robot interaction. We found that the story selection policy did personalize to each child over time, shown by the root mean square distance from the initial policy and the rate of matching maximum reward state action pairs in the Q table between 2 policies. Children who interacted with a personalized robot learned and used significantly more target words compared to the non-personalized and baseline groups. We also found that children's engagement cues are significantly correlated, and that this trend was driven by the personalization condition.
At the crest of the hill stood a bear blinking blearily outside his cave.
They went to the crest of the hill and found a bear standing. And he saw a bear and he was really scared, so...
Children in the personalized condition attempted to answer the robot's questions more often, and this tendency was also reflected in their affective arousal cues. Analyzing children's electrodermal activity and body pose revealed that children in the personalized condition showed significantly higher attention and engagement levels throughout the sessions. With a relatable social robot companion, we have demonstrated that when we match young students with a learning partner that can grow and engage with them, those students flourish. In the fall of 2019, we plan to install our robots in kindergarten classrooms as part of their regular curriculum to study the long-term social impact of personalizable AI and robots.
I'm really good at math.
All right, so I hope you can get an appreciation. There's a lot of algorithms under the hood of that fluffy robot, and we can actually show really substantial gains in terms of vocabulary and oral language and engagement. And we look at skin conductance and video and what they're saying, all kinds of things, right? So there's a lot of rigor with which we're going about this. We're basically now gearing up towards 6 months deployment now in Georgia, working in public schools in Atlanta, Georgia. So again, the goal is to go longer deployments, more diverse learners, and show the impact, because our belief is that this could be a transformative technology and help. I mean, basically, a lot of it's around social justice, right? If you can't even get a decent education, what chance do you have, right? So a lot of this work is motivated by just the social justice of quality education for everyone. So interestingly, when we don't just look at kind of the personalization around the content, but the personalization around these social and emotional factors, we see when we've developed assessments where we can get a read from children in terms of how close do they feel to the robot? How emotionally connected do they feel to the robot over time? And the kids who rate a closer relationship with the robot correlates with higher learning gains. So that's interesting, right? We know this is the case for people, but we're starting to see the same psychology between children and robots, right? So if robots feel closer to the robot, they learn more. We're also seeing that personalization seems to be a boost on everything. So if you see that trend of closer to the relationship, the more they learn more, with personalization, you see that even more extreme. So it's interesting how personalization and these interpersonal dimensions are interacting. And this is things we're discovering right now. I think even within the field of psychology, developmental psychology, they probably haven't studied this in depth because it's hard to come up with a controlled stimuli, meaning the robot, who can run these randomized controlled trials to really get at the science of this, right? So again, I think a lot of this work is also providing new insights for how kids learn. One of the other things we're discovering is, so children learn from others in all kinds of ways. I mentioned that a lot of the way we teach is through this explicit tutelage or lecturing, like what you're getting now. But peer-to-peer learning, we know that children learn all kinds of things from their friends, not only knowledge and skills, but attitudes and things like that, right? So I'm just going to play this video for you, and there's a moment I want to draw your attention to, where the child and robot, they're playing a vocabulary game. It's called Word Quest. So there's a challenge word. In this case, it's lavender. There's a story scene with a bunch of stickers, and the child and the robot go across this scene and try to find stickers that match or satisfy kind of what lavender is. So first it's the child's turn. I want you to kind of pay attention to how she's relating to the robot during this, and then it's the robot's turn.
What are we trying to find?
We are trying to find lavender color stuff.
Okay. The
That's not
word
lavender.
was lavender.
So first of all, just notice how she's positioned the robot, right?
What is
There's a
lavender?
strong affiliation going on there just by the body language the child has with the robot.
Girl.
So
Something.
she chooses a sticker. Turns out it's not right.
I'm sure you will do better.
And so the
next
robot gives her
time.
encouragement.
I believe
Says, I believe in you. She's a little disappointed, right? But you see that affiliative gesture,
Time to
and she's
perform.
right back in it. So it's the robot's turn,
Is
but she is
purple.
highly engaged. And you can see she's touching the robot, she's leaning into the robot. She's also trying to find things, even though technically it's the robot's turn.
Flower.
I believe.
And then she says back to the robot, I believe in you,
The
right?
flower is
So these attitudes of
purple.
empathy
It
and
has the
support,
color
she's
lavender.
picking up on simply because it's the behavior the robot exhibits, right? The robot's not telling her you should be supportive and empathetic. The robot's just being that way, and she is socially emulating the robot's behavior. So this is really powerful when you think about it, right? Because being a successful student is not just about having the skills and knowledge. It's also all these really important learning attitudes, right? So being able to get along with your friends, having a growth mindset, really believing that you get better through effort, not just that you're either good at something or bad at something, and that's just the way you are. So we've been starting to push this concept of, will children actually learn other kinds of attitudes like mindset and curiosity by playing challenging games with the robot that just happens to exhibit these qualities itself? So we've done other studies now where we have a randomized controlled trial, say, where the robot is solving tangram puzzles with a child. We develop a model where the robot is really solving the tangram puzzles, so it's learning with the child really as a peer. And depending on the condition, the robot is exhibiting growth mindset behaviors like, this game was really hard and I might not have succeeded on this puzzle, but that's okay because that's how I get better. Versus a robot that may have what we call a more neutral mindset, which just might be making factual comments about this puzzle is taking me longer to solve than the last one, right? So one is expressing a growth mindset, the other robot condition would express what we call a neutral mindset. We didn't think it was ethical to have a robot exhibit a fixed mindset because that's not good for kids, so we didn't do that condition. But the punchline is, so we've looked at this, we see in a short-term encounter, in fact, on these challenging puzzles, not only do children pre-post start to self-identify with growth mindset, if they play with the growth mindset robot, on the challenging puzzles, and we intentionally have unsolvable puzzles so we can see how hard the child tries on them as part of our intervention. And we see them actually demonstrate more grit. So what we've also now done is a long-term study where we've looked at both curiosity in addition to mindset, and what we're seeing is that over repeated encounters, curiosity will increase over time, but after a month delayed post-test, it goes back down. But when you combine curiosity with growth mindset, both stick. So the growth mindset interacts with curiosity and these other attitudes in a really interesting way, right? So again, we're doing a lot of not only advancing AI and kind of the role of robots and understanding how children learn with these kinds of robots, we're learning a lot about how children just learn, period, right? So again, there's a lot of psychology behind this work. So this is just a video now of, we've done the study, it's 3 months later. There's, a mystery puzzle. You have a simpler puzzle that kids know they could solve. You have a more harder puzzle, and then you have a mystery puzzle. And what we see is the kids are much more likely to want to take the challenging puzzle or the mystery puzzle. And you ask them why, they're saying things like what the robot said. It's like, I love to be challenged. I learn through, I'm curious. I want to try things that are things I don't know how to solve, right? So children are verbalizing the same kind of attitudes and making the same kind of choices. Again, in a delayed post-test as they did with the robot. So again, this is really, it's fascinating. It's really fascinating. The beauty of this is that it doesn't matter what the game is, right? You can layer all the social relational stuff on top of that with the learning companion technology. So it's so different than learning games on a tablet or behind a computer, right? It's a very different kind of learning process, but I think for kids it can be a very powerful one. So we're revolutionizing a lot of stuff. So now I'm going to shift gears and I'm going to talk about AI education, so helping kids learn about AI. We've already talked about a lot of this in the preamble. We need an AI literate society for all of these reasons. So the question is, what do you do about it? So we've started studying how young children think about these smart devices because, Alexa's coming into the home, Google Home's coming into the home. And what do they think about these technologies? So this is an excerpt from an interaction where we brought kids in to interact with a wide range of smart toys and smart devices and kind of smart apps. And this is one interaction where a girl picks up, goes to an Alexa and says, Alexa, what is sloth seed? And Alexa says, I'm sorry, I don't know how to help you with that. I'm sure many of you have heard that from Alexa. And she says, oh, that's okay. And she picks up another Amazon Echo. I'll see if this Alexa knows. Okay? So it's pretty clear kids don't really understand how these technologies work. And you can imagine that that can be an issue. We've looked at younger kids versus older kids, and we'll even ask them questions like, who's smarter, you or Alexa? We see younger kids thinking that they're still smarter, but we see older kids, like 8 to 10, saying that Alexa's smarter. Well, that's a problem because actually Alexa's not smarter than a person, and you want to make sure that kids have a healthy relationship with these devices, especially if you think about, you saw with the robots, if a robot can shape children's attitudes, another word for that would be, this is a very persuasive technology. If you have AI being able to form these social and emotional relationships and leverage the social psychology, you can create, in principle, an incredibly persuasive technology. And if that's the case, you can imagine companies manipulating that in all kinds of ways to get you to do stuff that maybe is not in your best interest, but it is in the company's interest, right? So this is, again, kind of a future we don't want to have happen. We want to make sure people are cognizant and savvy about these kinds of things. All right, so we've started to take platforms like Scratch and App Inventor, which I'm sure many of you have used, and we're taking cognitive services, things like sentiment analysis and speech recognition and machine learning for, supervised learning for vision models for object recognition, and we're putting those into these platforms so kids can learn about those technologies as well as use them in their own projects, right? So here's a video of a school where we've been doing one of our workshops.
Robots. You could play rock, paper, scissors.
So this is an activity where kids program
rock, paper, scissors
a computer to play rock, paper, scissors,
and on shoot, you did one of the motions.
where they train
And
it
the
through
camera did
vision
one of
and
the
other
motions.
images how to recognize the hand
Rock,
gestures. So we're applying
paper,
supervised machine learning
scissors, shoot.
to train that.
The
And then
computer
they're
gets better as
designing
you play the
the
game.
algorithm by
It's
which
like
the computer
might
actually
not
gets
know everything
better
at first,
over
but
time.
If we keep trying, we get
Through
better.
iterations, it's tracking your
Everyone has heard
behavior
about like
and trying to
machine-based
predict it.
learning or artificial
So it gets better.
intelligence. And there was a certain no questions asked for a lot of the more tech-savvy parents. It was like, go for it.
Technology is going to be a huge part of their lives, much more so than my life. If it's scary for some people, this AI technology, I totally get it. But as a parent and as a teacher, I thought it was really important because these are skills that 21st century kids need to have.
When my dad was young, he bought a car and took it apart to see how it worked. So you teach people that young how these things that grown-ups mostly program, how it works.
So again, you hear expressions of parents saying, AI's scary, we don't understand it, but then also recognizing kids need to understand this stuff. So this is what I would call educational research, right? So there's no standards for K-12 AI education. There's actually a committee I'm part of now trying to create those standards. There's no curriculum for K-12 AI. None of this exists, right? So we are having to create it from scratch is the punchline. So there's a lot of interesting research questions that we ask as we try to build not only the curriculum and the projects and the assessments and the teacher training guides, everything that's needed in order to help bring these kinds of learning experiences into schools and to after-school programs. So we're talking about kids as young as preschool all the way up through high school. So of course there's a very natural question, just based on children's natural development, what kinds of concepts can kids understand about AI at different ages? That's an open question, right? What are the most effective curriculum approaches, right? You know, there's lecturing like this, but you know, at MIT we believe you learn best when you have hands-on learning and you work in teams and you develop projects that you care about, right? So we are championing a constructionist approach, but there could be other effective approaches. As you've been seeing, we have a question about what does learning about AI change your attitudes about AI? Do you fear AI? You know, do you understand that AI systems can be biased and how to design them in a way to not be biased? All these kinds of things, right? This is important. How does AI change your perception about themselves? Do they now see themselves as people who can create these technologies? Not just use them, not just other people do it, but that I can do it. That's really important. And then, you know, through these activities, as you know, because you're doing the BeaverWorks program, you can learn all kinds of things. You can learn about ethics, you can learn about teamwork, you can learn about communication skills. You want to, you know, kind of, again, think about the whole student as you're designing all these activities. So I'm going to highlight a couple different projects. So this is Randy Williams. She's a first-year PhD student in my group right now. She developed for her master's thesis an early AI education curriculum called PopBots. So you may recognize the face is the same face as the Tega. So like we have developed all this cool technology to run on an Android phone that we can put in a robot chassis. Well, we can take that same app and that same technology and allow kids to build Lego robots, and now they've got this cool social robot that now they made, right? So again, a lot of this is about making these advanced tools and technologies accessible to children. One of the things that we're also finding that's really provocative is that, especially when you're talking about young children, an interesting way for children to get insight about how machines learn is by having the machines explain what it's thinking, right? So again, this is like social robots as an AI educational intervention, where this again is for preschool students. They're teaching a robot how to recognize healthy versus unhealthy foods. There's a lot of metadata for those foods. It's actually using K nearest neighbors. The child doesn't know that, but that's the algorithm. And if the robot does something like blueberries are not healthy, and you're like, oh, so why is that? Let's ask the robot. You can ask, why do you think that? And the robot explains it. And then you're like, the child implicitly is starting to understand, okay, this is how the robot's making sense of these examples. This is how the robot's actually learning. And so again, it reveals the underlying algorithm. So again, we're trying to think about these new paradigms to help kids learn. So in Randy's initial curriculum, we basically exposed, again, preschool and kindergartners to things like knowledge-based systems. So that was rock, paper, scissors. Generative AI, I don't know how many of you are following GANs, but you know, AI is starting to get very creative, be able to generate things that you know, a human may have guided and shaped kind of the space of things it can generate, but it's creating things that people themselves didn't create. So we're trying to expose children to that idea that AI doesn't always just follow the explicit rules like code. It can generate things you didn't explicitly code, right? And supervised machine learning, which is the food set you saw. So we're looking at, do they understand the algorithms at an intuitive level, right? But then also, if you're programming a robot to play rock, paper, scissors, that's an opportunity to say, how should the robot behave when it wins? How should the robot behave when it loses? Maybe that's a chance to think about sportsmanship, right? So there's a lot of things we're trying to weave into, social emotional learning, as well as kind of the programming and the conceptual understanding of kind of the intuitions of how these algorithms work. So we've been running these workshops now in Somerville and Boston Public Schools. This particular project we ran with 80 kids. 5 half-hour sessions in after-school and classroom sessions, often facilitated by a mentor. But kids basically build their social robot, and they go through these activities. And then we have these assessments we've been creating, these kind of very child-friendly assessments of questions that they can do on a tablet that gives us a sense of, well, so what's sticking? Are they learning or not? And so you're just seeing, basically this is an indication that on some things, kids are definitely more or less getting it, and some more confusing. Maybe that's because we're not doing our job right. Maybe it's more too advanced for children of that age. That's the point of continued investigation, right? So this is very much about research, right? We don't know how to do this the best way. We're trying to figure it out, and we're doing it by co-designing and deploying and learning and iterating. And I'm sure as you're learning, this is how you design stuff. This is how you make stuff that works. You have to get it out there, have your stakeholders work with it, learn and iterate. So what we do see, though, is that when children spend more time and explore more with the toolkits, these activities, they definitely learn more. So that's promising. It's like these activities are actually helpful and well designed, that if the children really spend time with them, they actually really do learn a lot better. So now we're starting to think about older kids. So now we've been developing, Gen AI is for Generation AI, like what's after Generation Z, well, Generation AI, for 3rd and 5th graders. So now we're developing simple robot kits where we're looking at a combination of both online, plugged, kind of using robots and hardware activities, but also we're learning from a lot of teachers that having a repertoire of unplugged, meaning it doesn't require a computer at all, is also important because teachers today, they don't know AI. So there's a huge adult capacity building question here of how do you help teachers understand this stuff and feel comfortable enough about it to introduce it. Well, some teachers aren't going to feel comfortable with having a lot of computer work, but that doesn't mean they can't start introducing this in other ways, right? So unplugged activities as well as technology-based activities. And again, a lot of this is about the research of how we bring all of these things together. So now we have over 20 hours of content where we conduct workshops that are often in the form of one full week for 20 hours plus a lot of design time, a lot of like what you're doing right now in your curriculum, where we have a lot of modules going from like introduction to programming, introductions to AI and robotics, simple machines, electronics, and then getting into artificial intelligence, right? And there's a bunch of modules we've been creating. These are examples of ones we've created for AI, chatbot, machine vision, machine learning, things like that. This is the PopBot robot. You can see it's meant to be a very inexpensive kit-like robot. It's based on an Arduino. We've added Arduino or leveraged Arduino extensions into Scratch so that basically all of our activities are happening in Scratch and you can talk to the robot from that. We're adding external cameras and other sensors so we have richer visual input. Basically, kids can create their own project after going through all of these activities of their own choosing. So I'm going to show a video of one particular child. So we've been piloting this now, 82 kids in Somerville schools. This is Ozzy.
My name is Ozzy.
How old are you?
8 years old.
He's 8.
I made a baby seal because I like creatures that are from water and also because it was a cute thing. On a video, we were looking and we saw a baby seal and I decided, well, that's what I wanted to make. So we made that robot. I programmed a robot how to make sounds, movement, and feeling. For a course that
So he's training, machine learning models recognize fish-like things from non-fish-like things.
Do you want to set up the fish so we can run it?
probably gonna fall.
And then when the robot sees the fish, you see, I found one, the hearts, the peers, et cetera, et cetera. So he's 8, right? He's using machine learning in his own project, inspired by Harp Seals. He loves Harp Seals. So this is cool, right? I can tell you when we started this work, we were told point blank, you can't teach kids about AI. You have to wait until at least high school. And we're like, nonsense. If you can start learning math in preschool, you can start learning about AI in preschool. The question is just how do you do it? So we're at MIT. We're in an amazing place. We're at the forefront of AI in so many ways. So this is another project where we've been collaborating with Antonio Torbala, who is the director of the MIT Quest for Intelligence. So that's our big, MIT-wide initiative on AI. And he's an expert in GANs. Who knows what GANs are? Generative Adversarial Networks. Okay, so he's doing cutting-edge work in GANs. So GANs are pretty amazing now. So they can generate things that can be as good or better than what people do. So here's an example of 3 faces. So the question is, how many people think this face here is a real person versus something created by the GAN? This one here. Real or generated by GAN? Real? Fake? Fake? All right. Well, so they're all generated by the GANs, of course. All right. So, so one question then is, how can you get more control over GANs, right? So much kind of like in the human brain, there's a sense of our visual system has these different neurons that can be trained to recognize different kinds of entities. How can you train GANs to get that more kind of modular, controllable feel about it, right? So this is the work of Antonio Torbala. He can actually train it so that, when you're training on something like images, these are like churches, he can actually show you that different neurons in the GAN respond to different features. So domes, clouds, trees, grass. And so this is amazing now because he can actively, he calls it Gann Paint, he can effectively paint quasi-photorealistic images by turning features on and off. So that's pretty cool, right? So, you can paint, I want a tree here, I want some sky cloud here, I want a different kind of dome, That's pretty amazing, right? So these are GANs. So if we want to teach kids about GANs, this is a really cool way to teach kids about GANs, right? So we're working with Antonio to start to bring it into Scratch, right? Literally, we're bringing this stuff into Scratch. So we've been looking at, we figured, churches, probably isn't the most kind of neutral subject matter, so we're actually retraining it on castles, but the same kind of features, where now kids can learn about GANs and use GANs in their own projects. Because a lot of people in Scratch want to create video games and artwork. So what if you could use GANs to create really cool artwork for your Scratch project, right? We're also looking at things like style transfer, right? So this is the other cool thing. So can you train on zebras so you can texture map stripes onto any kind of animal? Or can you have a winter scene and turn it into a summer scene, right? So that's the punchline, is, because we're at MIT, we're able to take this really cutting-edge research that literally is just getting published right now and putting it in the hands of kids. So the last thing I want to touch on is ethics, right? So we want to make sure that kids growing up today not only understand these cool techniques and can use them, we want them to be able to think about the ethics and the fairness of what they create. So, again, there's been a lot of stuff in the media, if you've been reading it, around AI systems that have not been behaving in a particularly fair or unbiased way, and that's a big issue. And we're starting to understand why that is, and a lot of it is around the training data, right? So we want children to be conscientious consumers and designers of AI systems. We've started to develop an AI and ethics curriculum for middle school, where our philosophy is, as opposed to saying you're going to learn about AI and program robots, and that's cool, and then learn about ethics at the end, we're going to weave it all together to make sure that you get your healthy dose of ethics as you learn about these methods and technologies, right? So, as we're thinking about GANs, we're thinking about, well, so there's a lot of ethical questions around GANs, like deep fakes. And when you talk about, the future of music, who gets credit if you're an artist who spent a lot of time with a GAN tool generating a lot of your music, right? So it's there's a lot of interesting questions that come up around GANs that we want to introduce as they learn about GANs. We've been developing a middle school curriculum where we've been covering a range of topics, things like supervised learning and how data sets can bias the outcomes. And we've been looking at YouTube as a capstone and recommender systems, right? So why middle school? Kids are already on social media. They have their phones. They're touching AI every day. They need to understand that. And also just developmentally, they're at the point where they can start to, understand and engage in, more sophisticated concepts of their moral development. So we developed a week-long workshop. We literally just piloted here at the Media Lab a couple weeks ago. There's roughly 11 activities. This was a pilot we did with 3 days of activities where, again, they learn about, we use Google Teachable Machines, which is a really great intuitive way to train machine learning classifiers. We actually provide kids with a biased data set to recognize cats and dogs. So cats are very diverse, whereas dogs were much, a much narrower sense of what a dog looks like, and many of them look rather cat-like, so kids learn, hey, it's much better at recognizing cats versus dogs. And then we play Joy Bellamy. I don't know how many of you know Joy Bellamy's work, but she founded the Algorithmic Justice League. She's done a very deep analysis of the performance of face recognition systems across men and women, across different skin tones, and has found that those systems do not perform the same across those groups. So they tend to perform the best on white men and the worst on black women is the punchline, dark-skinned women. So this is an issue because it means those systems aren't going to be as fair if they don't perform as well, right? So she's highlighting these issues of bias, and it's because those groups were underrepresented in the data set, right? So kids are learning about these topics. They're learning that when you talk about machine learning where you're trying to optimize something, like if you're going to make a peanut butter jelly sandwich, that's one thing. When you say, how do you make the best peanut butter and jelly sandwich, you're starting to encode an optimality criteria that is, in effect, an opinion, right? Because what's best when it comes to a peanut butter jelly sandwich? It could be the tastiest, it could be the healthiest, it could be the most convenient, it could be any number of things. People assume that algorithms are objective, and they're not, right? Especially when you're applying machine learning. It's what are you optimizing for, right? So they're starting to appreciate all these questions. And then they're starting to look as a capstone at YouTube recommender systems. So why did we choose YouTube? Kids, middle school, they love YouTube. They spend a lot of time on YouTube. They're extremely knowledgeable about YouTube. And there's been a lot of questions and concerns about YouTube, right? So there was a TED Talk on, I don't know how many of you heard about ElsaGate. So Elsa from Frozen, because when you have the automatic recommender system feed videos for the kids stuff, it's like you start with kind of Elsa videos, but they can get pretty unsavory if you let it keep going. That's inappropriate for kids, right? So this stuff, it's like there's a lot of ethical questions, right? So here's an example of a workshop. This is an unplugged activity, right? So this is where if you're a teacher and you're not comfortable with computers, you can still do this with your class. So is there volume? So anyway, okay, so there's a number of tools. So there's a very fast-growing field around ethics and AI right now. And there's a number of frameworks that are being developed that we're adapting now to kids, where one is called the Stakeholder Matrix, right? So when you have a diversity of stakeholders, different stakeholders favor different outcomes more than others. And this is just reality, right? If you're Google, you're going to favor profit is really important, versus if you're a content creator, you want people to see your stuff, versus if you're a viewer, you want entertaining stuff that's relevant to you. And sometimes those values of the stakeholders conflict and you have to make trade-offs, right? So we introduce kids to these kinds of tools that they can reason about it. So a lot of this is guided and facilitated by a mentor asking questions like, how does YouTube make money? They understand ads. So again, I mean, one of the things we're consistently impressed by is the deep knowledge children have on YouTube. But you can engage them in pretty sophisticated debates because of this. And then we go through an exercise, this is a Stakeholder Matrix, where they can design their own YouTube. So here's an example of 3 different projects. They're paper prototyped, right? So one is polite YouTube. So you being able to have a feature where you can flag comments that are not nice, and maybe you want to hide those because you don't even want to see them, right? There's age-appropriate YouTube, where you may have a choice over what kind of recommender system you get to choose. Rather than just having the one recommender system, you decide which recommender system, and the recommender systems are optimized for different things, right? That was another project. The one that was our favorite was the less addictive YouTube. So these were kids that are like, we spend way too much time on YouTube. And so the idea was over time, it would literally, they use the word cringy. It would get cringier and cringier. So the user interface would get to be dull, grungy colors. You would start getting videos like nails on a chalkboard. That was basically your cue to say, you've been on YouTube long enough. Maybe it's time for you to go outside and play or do something else. So anyway, putting power in kids' hands to think about these things is really what this is all about. and kids come away really having a much, first of all, recognizing AI in their lives that they are using that they may not have understood before, understanding it is manipulable, right? These are things that people design. There's lots of decisions that go into them. These are things that they can change, and they just need to be cognizant of how these algorithms work in this ethical way, right? So lots and lots and lots of work. This is just kind of wrapping up. Again, we're taking this very holistic approach of preparing kids for success in the era of AI, looking at all these kinds of questions. We're starting to engage education nonprofits, training teachers. This stuff is starting to get out into the world right now. So maybe not too distant future, you'll be able to access some of these materials. And we would love to know what you think. All right.